If Q is the magnitude of net charge that crosses through any cross section of the conductor in time t, then the average current in that time is I bar equal to Q by T. If dq is the magnitude of net charge that passes through any cross section of the conductor in the small time interval dt from t to t plus dt, then the instantaneous current at the time t is I equal to dq by dt. A current 5 ampere flows in a resistor. How many coulombs of charge pass through the resistor in time 3 minutes? So current is given, time is given, then magnitude of charge is IT, I given, time given, then it is coming 900 coulomb. This is 900 coulomb. This is 900 coulomb. The current in an electric circuit rises exponentially as given by I equal to 10 ampere 1 minus e to the power 2t per second. Calculate the charge flowing through the circuit in 250 millisecond. Q is equal to integration I dt, and the limit is from t is equal to 0 to t is equal to 250 millisecond. Then putting the I value and integrating, we get the required charge. In a metal there are free electrons. In the absence of electric field, the free electrons move at random. The average motion is 0, so there is no current in the absence of electric field or in the absence of battery. Think of this is the positive ion, this is the positive ion, these are the positive ion. In the absence of electric field, if you observe any electron motion, any free electron motion, it will move with a constant velocity. It will move with a constant velocity, collides with a positive ion. Then after collision, again it moves with a constant velocity. Again after collision, it moves with a constant velocity. So if you observe all the electrons, they are moving like this random motion. So the average velocity is 0. If electric field is applied, let electric field is applied this way, then between two collision, between these two collision, the electron velocity changes, it doesn't remain constant. Because of electric field, there will be a force acting, there will be a force acting this way. So because of force, there will be the acceleration this way. So as a result, the electron motion will not be a constant velocity between two collision, and the electron will move in the presence of electric field. The electron will move in the presence of electric field like this and strikes with this positive ion. Then after collision, it moves this way and strikes with this positive ion. Then after collision, it will move this way and strikes with this positive ion. In the absence of electric field, it was reaching here. Now in the presence of electric field, it is reaching here. So this much distance is the drifting distance. This much distance, the drifting distance. Accordingly, there will be a drifting velocity or drift velocity in the opposite direction of electric field. If you observe, before electric field, in this path, electron velocity, let it remains constant at u vector. Then in the presence of electric field, this velocity is u vector. But this velocity does not remain constant at u vector, and here the velocity becomes v vector. This v vector equal to u vector plus a vector t. T is the time between this collision and this collision. This u vector, that is not dependent on the electric field, but v vector depends on electric field through a vector. So u vector average was 0 before field. In the presence of field also, u vector average is 0. In the presence of electric field, v vector average, that is called drift velocity. And the drift velocity of the free electrons is opposite to electric field. Let us derive the expression for the drift velocity. The force on the free electron is minus E vector. The acceleration of the free electron is F vector by m. So it is coming minus E vector m. Electron's velocity just before a collision is v vector equal to u vector plus a vector t. T is the time between two collision. U vector is electron's velocity just after the previous collision. If we take the average of this, then v vector average is equal to u vector average minus E vector by m t average. U vector is independent of electric field, so u vector average remains 0 always. V vector average is called drift velocity. T average, that is the time, average time between two collisions, called mean free time or relaxation time. The symbol is here tau. So tau is equal to t bar. The drift velocity formula is then minus E vector by m tau. The magnitude of drift velocity is called drift speed. Vd equal to E by m tau. If we consider a cylindrical conductor, whose ends are maintained at a potential difference of V, whose ends are maintained at a potential difference of V, and the cylinder cross section at each end is an equipotential surface V2. This end is also an equipotential surface V1. And if L is the length of the conductor, then the electric field remains constant. Electric field remains constant everywhere inside the conductor, whose magnitude is E equal to V by L. Here V2 bigger than V1. So this E, if we put here, then the drift speed becomes EV tau by ml. This equation is applicable only for cylindrical conductor, but this and this equation, they are applicable for any conductor. Let us find the relation between electric current and current density in terms of drift velocity. This is a portion of a cylindrical conductor of cross-sectional area A. There is a uniform electric field E vector directed from left to right. Let there are n number of free electrons per unit volume, all moving with a drift speed Vd. So the electrons contained in the cylinder ABCD, they have crossed the cross section AB in the time from 0 to t. Their number is n into A into Vdt. Their charge is Q equal to minus Ne. So this is the charge. So the current is the magnitude of charge divided by time. So it is coming NEA Vd, and the current density, that is equal to current per area. It has the magnitude NeVd, and the current density is a vector quantity. It is directed along the electric field. So the current density is minus NeVd vector. Vd vector is opposite to electric field. J vector current density, it is along electric field. So there is a minus sign. If a current 5 ampere flows in a copper wire of cross-sectional area 1 millimeter square, find the drift speed of the free electrons. Assume one copper atom contributes one free electron. The density of copper is given. The atom mass of copper is given. J equal to NeVd. J equal to current by area. So it is asked to solve Vd. J we know. E already we know. If we solve N, then Vd can be solved. N is the number of free electron per unit volume. In the question it is mentioned one copper atom contributes one free electron. So that is why N is number of free electron per unit volume. That is number of copper atom per unit volume. If there are n copper atoms in V volume, then N is equal to N by V. Multiplying the atomic mass in the numerator and denominator. This is small m. Small m is the mass of V volume of copper. This mass by volume is the density. So N is equal to density by atomic mass. Atomic mass given 63.5 pu. We can convert to gram, and hence we can convert to kilogram. So N we can find then Vd is equal to J by Ne. The relaxation time of electrons is the average length of time an electron travels through a metal before it changes its momentum upon scattering. What is the meaning of this? This is a positive ion. This is another positive ion. In the absence of electric field, the electron moves with a constant velocity, constant momentum. When it strikes, there will be a change in momentum. So how much time the electron moves? How much time the electron moves with a constant momentum? That's average is called relaxation time. Ohm's law states that in a homogeneous metallic conductor at a constant temperature, the current I flowing is linearly proportional to the voltage drop in the conductor, that is I proportional to V. So I is equal to a constant into V. This 1 by R, it is called electric conductance, and R is the electric resistance. This statement of proportional is called Ohm's law. Vd we know EV tie by ml. I we know NEA VD. Let us substitute this VD here. Then we get I is equal to N square eta by ml into V. This N square eta by ml, this is equal to 1 by R, and hence R is equal to ml by N square eta. So I is equal to 1 by R into V, or V equal to IR. These are not Ohm's law. These are not Ohm's law. Ohm's law demands 1 by R has to be constant, or R has to be constant at a constant temperature. Then I will be proportional to V. Let us analyze whether this R is constant or this R depends on what factors. At a constant temperature, L doesn't vary, A doesn't vary. If we find at a constant temperature N and tau, they are independent of V, then this R remains constant. Then I proportional to V. This is Ohm's law. Ohm's law is not a general law in electromagnetism. It is a specific property of certain materials which are called ohmic or linear conductor. The materials which do not obey Ohm's law, they are non-ohmic or non-linear conductor. Many homogeneous materials, including conducting metals and alloy, at constant temperature obey Ohm's law for a certain range of values of applied potential difference. If the potential difference is very large, then everybody will behave in violation of Ohm's law. Objects like vacuum tube, thermistor, transistor, crystal rectifiers, they are non-ohmic. To verify whether Mn is ohmic or not, the circuit is this way connected. Closing the key, the current is measured by the ammeter, and the potential difference across Mn is measured by the voltmeter. By changing the contact point of rheostat, we can vary the current and accordingly the potential difference. If a graph is plotted between current and potential difference, and if the graph is a straight line passing through origin, then the conductor Mn obeys Ohm's law. If we consider a cylindrical conductor of length L, whose this end is an equipotential surface, this end is also an equipotential surface, so the potential difference is V2 minus V1. Then in this cylindrical conductor, everywhere inside the conductor, the electric field remains constant, the current density also remains constant. The magnitude of electric field is V by L, and the current density magnitude is I by A. I is the current flowing in this conductor, A is the cross-sectional area of the conductor. The resistance of the conductor is V by I. So V equal to IR, V equal to EL, I equal to J. So it implies V is equal to JAR, or E is equal to rho J, rho equal to AR by L. This is called electrical resistivity, formerly known as specific resistance. The conductivity of the material is 1 by resistivity. If the conductor is ohmic, then at a constant temperature, R is constant. So for a ohmic conductor, at a constant temperature, the conductivity and resistivity of the material, they also remains constant. If the conductor is isotropic, then E vector and J vector are in same direction. So J vector equal to sigma E vector or E vector equal to rho J vector. A 20-meter metallic conductor of cross-sectional area 1 millimeter square has a resistance of 10 ohm. Calculate the resistivity and conductivity of the metal. Conductivity the resistivity formula is AR by L. The conductivity formula is 1 by resistivity. So putting the value, we find the resistivity and we find the conductivity. 1 by ohm is called Siemens. 1 by ohm is called Siemens. Its symbol is capital S. Siemens is SI unit of electric conductance. The ratio of drift speed of charge carrier to the magnitude of applied electric field is called mobility of charge carrier. So mobility of charge carrier is Vd by E. We know Vd is equal to E by m tau. So accordingly mobility is equal to Vd by E. So it is coming E tau by m. The conductivity of the material of the conductor is J by E. J we know NEVD. So Vd by E is the mobility. So conductivity is Ne mu. Ne is the magnitude of free electron charge per unit volume. Ne is the magnitude of free electron charge per unit volume. The ratio potential difference V between the ends of a conductor to the current I flowing through it is called the resistance. So R is equal to V by I. The resistance of a cylindrical conductor is given by rho L by A. From this V is equal to IR. This is a general equation. It is not Ohm's law. This will be Ohm's law if R is constant at a constant temperature, then V proportional to I. A rectangular block of iron has dimension 1 centimeter, 1 centimeter, 20 centimeter. What is the resistance of the block measured between the two square ends? What is the resistance between two opposing rectangular faces? The resistivity of iron at room temperature is given. Resistance is rho L by A. The rectangular block is like this. So this is the square face. It is 1 centimeter, 1 centimeter. The length is 20 centimeter. So the first bit asked resistance of the block measured between the two square ends. So in this case, the length is now 20 centimeter. The cross-sectional area is now 1 centimeter into 1 centimeter. The next question is asked resistance between two opposing rectangular faces. So if I consider this is a rectangular face and other rectangular face that is not visible to us, then the area is now this rectangle area. So it is 1 centimeter into 20 centimeter. And here the length is now this much. This is now 1 centimeter is the length. If rho is the resistivity at temperature T and rho plus d rho is the resistivity at temperature T plus dt, then the temperature coefficient of resistivity at the temperature T is d rho by rho dt. D rho by rho is the fractional change in resistivity. In general, alpha varies with temperature. If we consider a small change in temperature from T0 to T, then in that small range of temperature, this alpha can be nearly constant. And if alpha into T minus T0 is very small, that means it tends to 0, then we can find from equation 1 alpha will be the average alpha, that is equal to rho minus rho 0 by rho 0 into T minus T0. Rho 0 is the resistivity at temperature T0. Rho is the resistivity at temperature T. Then rearranging this, we get rho approximately rho 0 alpha bar T plus rho 0 into 1 minus alpha bar T0. In general, this T0 is considered to be 0 degree Celsius or 20 degree Celsius. And this is the equation of a straight line with slope this much and rho intercept this much. The temperature coefficient of resistivity is positive for metal and alloy. So for metals and alloy, with rise of temperature, the resistivity increases. The graph is this way. For superconductor, the graph will be like this. For semiconductor, the alpha is negative. That means with the rise of temperature, the resistivity decreases. So this is the graph. The alloy manganese and constantan, they are used for making fixed resistor because for them the alpha is very small and positive. So that if changes in dimension of a conductor with changing temperature can be ignored, then the resistance varies with temperature according to R is equal to R0 into 1 plus alpha bar into T minus T0. We know alpha bar, that is the temperature coefficient of resistivity, rho minus rho 0 by rho 0 into T minus T0. Here in the question says by changing the temperature, the geometric dimension of the body doesn't change. So as a result, rho is equal to R A by L, rho 0 equal to R0 A by L. A and L are not changing, only R is changing. So putting rho and rho 0 in this equation, then rearranging, we get R is equal to R0 into 1 plus alpha bar into T minus T0. So this says this alpha bar is the temperature coefficient of resistance and this alpha bar is the temperature coefficient of resistivity. Both are same under the assumption of temperature changing, the geometric dimension doesn't change. An electric toaster uses nichrome. Nichrome is an alloy for its heating element. When negligibly small current is passes through it, the resistance at room temperature is 27 degrees Celsius, is 62 ohm. When the toaster is connected to 250 volt supply, the current settles after a few seconds to a steady value of 4 ampere. What is the steady temperature of the nichrome element? The temperature coefficient resistance of nichrome is given. An electric toaster uses nichrome. Nichrome is an alloy for its heating element. When negligibly small current passes through it, its resistance at room temperature 27 degrees Celsius is found to be 62 ohm. When the toaster is connected to 250 volt, the current settles after a few seconds to a steady value of 4 ampere. What is the steady temperature of nichrome element? The temperature coefficient of resistance is given. Let T1 is 27 degrees Celsius, T2 is asked. At T1 the resistance is this much. At T2 the resistance is R2 is V by I, V is 250 volt, I is 4 ampere. Then alpha bar we know R2 minus R1 by R1 into T2 minus T1. Then putting this T2 minus T1, we get 47 Kelvin, which is equal to 47 C degree. C degree means it is the change in Celsius. So T2 is 47 plus 27 degree C, that is coming 74 degree C. This we can solve also in another method. We can take T2 to be 27 degree Celsius, T1 question mark, this will be R2, this will be R1, then we can solve in the same way what is T1. Or we can solve also this problem in another method. T1 is 27 degrees Celsius. So R1 is R0 into 1 plus alpha T1. R0 is the resistance at 0 degree Celsius. R2 is R0 into 1 plus alpha T2. If we divide this equation and this equation, R0 will be cancelled out. Then we can solve T2. Putting T1 is 27, or we can solve T1 putting T2 is 27 degrees Celsius. The variation of resistance with temperature. This alpha is the temperature coefficient of resistance. This alpha bar is the temperature coefficient of resistance. This is the average temperature coefficient of resistance in the temperature interval from T0 to T. Same, just like the resistivity variation, the resistance variation is similar. What is meant by the EMF of a cell? This is think of a cell or battery. This end marked positive, it has high potential. This end marked negative is at low potential. A battery or cell or generator or dynamo, they are commonly called seat of EMF. So in the cell, there is electrostatic field from high potential to low potential. The cell or battery is a good conductor. It contains free electrons. The free electron must move from left to right. So within very less time, the negative side or the low potential side becomes neutral, and the positive side or the high potential side becomes neutral. This is not really happening. Why is this not happening? So we can think inside the battery or cell, there is another field from negative to positive. This cannot be the electrostatic field. This is the non-electrostatic field. The battery shown is in the open circuit. So in the open circuit, the net field is 0. So En vector equal to minus Ee vector. That is why no free electron moving from left to right or right to left. If we imagine a positive test charge moves this way, the work done by the electrostatic field is positive. The work done by the non-electrostatic field is negative. If a positive charge moves this way, the work done by the non-electrostatic field is positive. The work done by the electrostatic field is negative. The electrostatic field acts both inside the cell, also outside the cell. But the non-electrostatic field acts only within the cell. If a positive charge moves this way, the work done by the electrostatic field divided by the charge is the terminal voltage of the cell. If a positive test charge moves this way, then the work done by the non-electrostatic field divided by the charge is the EMF. This EMF was earlier known as electromotive force. Since it is not a force, now we call it EMF. EMF of a cell is the work per unit charge done by the non-electrostatic field when a test charge moves from low potential terminal to the high potential terminal through the cell. Actually, battery, generator, dynamo, they are commonly called by seat of EMF. EMF was earlier known as electromotive force. Electromotive force is not a force, so we replace this name by EMF. Similarly, the terminal potential difference or terminal voltage of a cell is the work per unit charge done by the electrostatic field when a test charge moves from its high potential terminal to the low potential through any path. It can be inside the battery or it can be outside the battery. But to define EMF, the charge has to move through the battery or the cell, because the non-static field acts only within the battery or cell, but the electric field acts inside the and outside the cell. V is the terminal voltage or terminal potential difference of a battery. E is the EMF of the cell or battery. Capital R is the external resistance, small r is the internal resistance of the cell or battery, or generally called the seat of EMF. So V is related to the EMF. V varies with EMF, external resistance and internal resistance. Internal resistance increases with time of use. More the time of use, R will be more. EMF of a cell that always remains constant, it never changes. Consider n number of resistors connected in series, and this series group of resistors is connected across a battery that provides a potential difference of V. Here, same current I flows through each resistor. The potential difference across first resistor is V1 is IR1. Similarly, potential difference across second resistor V2 is IR2. V is V1 plus V2 up to Vn, and putting this value V is equal to IR1 plus IR2 plus up to IRN. This series group of resistor behaves as a single resistor of resistance R, the current I and the potential difference V. So V is equal to IR, then R equal to R1 plus R2 plus Rn. Consider n number of resistors of resistances R1, R2, Rn connected in parallel, and the parallel group of resistors is connected across a battery that provides a potential difference of V. Here the potential difference of each resistor is same and is V. Let I1 is the current through first resistor, I2 the current through second resistor, and so on. So I1 is V by R1, I2 is V by R2. This parallel group of resistors behaves as a single resistor of resistance R, potential difference V, current flowing I. This I is I1 plus I2 plus IN. So upon putting the values and I is equal to V by R, we get 1 by R equal to 1 by R1 plus 1 by R2 plus so on, and R is 1 whole divided by 1 by R1 plus 1 by R2 plus up to 1 by Rn. 2 ohm, 3 ohm, 6 ohm resistors are connected in series and parallel. Calculate the total resistance. In series combination, R is equal to R1 plus R2 plus R3. In parallel combination, R is equal to 1 by R1 plus 1 by R2 plus 1 by R3. At what value of the resistance X in the circuit shown will the total resistance between A and B be independent of number of cells? Here cells means groups. Cells doesn't mean here battery. So this is possible if this point is A, this point is B, this cell, if resistance of this cell is X, then the total resistance between A and B, is independent of the cells or groups. So it is only possible if the effective resistance between small a and small b should be equal to capital X. So the process is this should be equal to X. 2R, X, they are in series. That effective is in parallel with R. So the total effective between A and B is this much. This should be equal to X. Then upon rearranging and solving the quadratic equation, we get X equal to 2 whole into root 2 minus 1 R. This problem is for you. You solve by yourself. Kirchhoff's first law or junction theorem or point rule or Kirchhoff's current law, we can say KCL, states that at any junction in an electric circuit, the total current entering the junction must be equal to the total current leaving the junction. At the junction O, 5 conductors meet in this example. I1, I2, I3 approach towards the junction O, I4 and I5 leave the junction O. So first law demands I1 plus I2 plus I3 equal to I4 plus I5. This can be written I1 plus I2 plus I3 minus I4 minus I5. We can say I4 leaving, or we can say minus I4 is entering towards the junction O. Similarly, I5 is leaving, we can say minus I5 is entering towards the junction O. So this equation says the algebraic sum of currents at the junction is 0. Kirchhoff's first law statement either can be this or can be this. Kirchhoff's first law is a restatement of conservation of charge. Kirchhoff's second law or loop rule or Kirchhoff's voltage law KVL we call, states that the algebraic sum of changes in potential encountered in a complete traversal of the closed circuit or loop must be 0. Before applying this rule, you know if this is a resistor, if current flows, you know this side is high potential and this side is low potential. If we move this way, traverse means move. If we move this way, current flowing. If we move in the direction of current, then the change in potential is negative IR. In the opposite direction it is plus IR. Similarly, this is a sheet of EMF. Of the sheet of EMF, this plus is at high potential, this minus is at low potential. This is the direction of EMF. The direction of EMF is from negative to positive. If we cross or traverse the sheet of EMF in the direction of EMF, then the change in potential is positive. Change in potential is positive EMF. In the opposite direction it is negative EMF. And you know change means final minus initial. So final is always initial plus change. This shows a complex circuit. In this circuit, here two cells or two sheet of EMF and some external resistances. This R1 is the internal resistance, E1 is the EMF of this battery, E2 is the EMF and R2 is the internal resistance of this battery. When you find in a circuit there are many cells or battery, you take any one cell as the master cell. Now let us think this is our master cell. Then from this cell positive terminal the current we have to start. Then according to Kirchhoff's first law, how much current reaching, same has to leave. So I is flowing up to C, then at C the current has to leave also I. So this way current leaving I2, this way current leaving I1. So I2 plus I1 must be equal to I according to Kirchhoff's first law. So in the path CBA current is flowing I2. In the path CDA current flowing is I1. Both I1 and I2 merge at A and becomes I and flows along A to C. Let us consider a path. Say A, C, D. At A, the potential is VA. So we are at A, our potential is VA. This is zero resistance wire. So what is the potential here? Same potential here, same potential here, same potential here. So we are at A, our potential is VA. Now let us move the path ACD. So when we move this way, our potential remains constant at VA. Then when we reach here, our potential is not VA. So what is the potential now? This is the initial potential VA. This is the final potential we need. Final potential is initial plus change. We are crossing the resistor in the direction of current. So when we are here, our potential is then VA minus IR4. So we are here, our potential is VA minus IR4. Here also VA minus IR4. Here also VA minus IR4. Then when we will reach here, our potential is not VA minus IR4. We cross now a resistor and the EMF. Let us first think of this is the resistor. So we cross the resistor in the direction of current. So the change in potential is minus IR1. Also we cross the EMF. So the change in potential is plus EMF. Why is it plus E? Because when the sheet of EMF is traversed in the direction of EMF, that is from negative to positive, then the change in potential is E. So we are here, our potential is VA minus IR4 minus IR1 plus E1. Then we will cross this battery now. When you cross this battery, then we cross the resistor, also we cross the EMF. And in this path current flowing is I1. So when we are here now, our potential will be this much plus some change. What are the changes? Minus I1 R2, then minus E2. So we are here, our potential is this much. Then we will cross this resistor R3. When we reach here, our potential will be this much plus the change is minus I1 R3. So finally we reached at D. At D our potential is this much. So this is equal to potential at D. This way applying to a closed path, ACDA, then we will get the equation VA plus the changes in potential is equal to VA. Cancelling VA from both the sides, the algebraic sum of changes in potential in the closed circuit ACDA is equal to 0. So this is according to Kirchhoff's second law. Kirchhoff's second law is the statement of conservation of energy for the electric circuit. Wheatstone bridge is an electrical circuit that forms the basis of most of the instruments used for measuring resistance. The instrument that you are using in the lab for measuring resistance, they are the meter bridge, they are the potentiometer, they are the post office box, They work on the principle of Wheatstone bridge. The Wheatstone bridge arrangement is shown here. Let the current distribution is by the Kirchhoff's first law. I, then I1, I minus I1, I1 reaching at B, let divided Ig flows through galvanometer of resistance G, and I1 minus Ig flows through resistance Q. Ig reaching I minus I1, they merge, they become I minus I1 plus Ig that flows through X. Applying KVL to ABDA, we get this equation. Similarly, applying KVL to BCDB, we get this equation. If the potential of B and potential of D are same, then current through galvanometer is 0. Under this condition, the bridge is said to be balanced. So Ig putting 0 here and Ig putting 0 here, then we get equation 3 and equation 4. On comparing equation 3 and 4, we get R by P is equal to X by Q, or X is equal to Q into R by P. And the potential difference VA minus VB, we need the potential difference VA minus VB. Let I current flows, then I equal to E by R plus R. So if I follow the path B to A along this way, then VB minus IR plus E equal to VA. This implies V equal to VA minus VB equal to E minus IR. Putting the I value, we get V to be this much. Instead of moving along this path, we can also move along this path, or we can move also along this path. If we move along this path, then it will be VA minus IR equal to VB. This also implies V equal to VA minus VB, the same result. Find the potential difference VA minus VB. Here two cells are. We can take anyone to be the master cell. As I told earlier, the cells have no internal resistances, or you may think this R1 as the internal resistance of this cell, R2 is the internal resistance of this cell, which are for simplicity shown to be outside the cell. Or you may think the cells have no internal resistance, this R1 R2 they are the external resistances. Let us think this cell to be the master cell. From the positive terminal, let I current flows. Applying first law, Kirchhoff's first law, the I will flow this way by KVL VA minus IR2 plus E2, no internal resistance, minus IR1 plus E1 equal to VA. Then we solved this much. Then in the path AB, you can move the path AB either this way, or you can move the path AB this way. So let me move the path AB this way. So VA minus IR2 plus E2 equal to VB. This. Then VA minus VB how much? Then put the value of I here and rearrange. Then after putting the respective value, we get VA minus VB to be 0. Consider n number of cells connected in a series. This series group of cells is connected across an external resistance R. E1 is the EMF, R1 is the internal resistance of the first cell, E2 is the EMF, and R2 is the internal resistance of the second cell, and so on. This series group of cells is equivalent to a single cell of effective EMF and effective internal resistance. Let I is the current flowing. Then by Kirchhoff's second law to this path, En minus IRN plus E2 minus IR2 plus E1 minus IR1 minus IR equal to 0. Then solving I is E1 plus E2 plus En by R1 plus R2 plus Rn plus R. Applying Kirchhoff's second law to this closed circuit, and we find I equal to E effective by R effective plus R. Comparing these two equations, E effective is this much and R effective is this much. If all the cells are identical, then E1, E2, En, each is E, so this is Ne. R1 equal to R2 equal to Rn equal to R, so this is Nr. So I becomes then Ne by Nr plus R. If in the series group of n identical cells, x number of cells are wrongly connected, then how to solve it? One cell, second cell, third cell, fourth cell, let fifth is wrongly connected, sixth is wrongly connected. This is the external resistance. Let the current flowing is I. Then applying Kirchhoff's second law to the closed circuit, the first cell gives the term E minus IR, then plus the second cell E minus IR plus the third cell E minus IR plus the fourth cell E minus IR plus the fifth cell minus E minus IR plus the sixth cell minus E minus IR equal to 0. So this E cancels, this E cancels. So the total EMF becomes 2E. So how many terms are cancelled? 2 cells are wrongly connected, 4 are cancelled. Similarly here, out of n cells, x are wrongly connected, so 2x is cancelled. So then I equal to n minus 2xe, but there is no change in R term. That is why I equal to n minus 2xe by nr plus R. This cell and this cell, they are connected in parallel. Let I is the current flowing, then I minus I1 and I1 this way. These two cells behaves as a single cell of effective EMF, internal resistance. Let I1 current is flowing, here I1 flowing, here also I1 has to flow. Then by KVL to ABCF, the equation is like this. Then applying KVL to ABDE, the equation is this. Putting this value of I in the equation 1 and rearranging, we get I1 to be this much. The parallel group of cell is equivalent to a single cell. Applying KVL to this circuit, then I1 is E effective by R plus R effective. If you compare this equation with this equation, then E effective is this much and R effective is this much. In the parallel grouping of cells, if E1 equal to E2 equal to E, then the effective EMF is E. If R1 equal to R2 is equal to R, then the effective EMF is E1 plus E2 by 2. If E1 equal to E2 equal to E and R1 equal to R2 is equal to R, then E effective is equal to E. and R effective is equal to R by 2. So when the cells connected in parallel and if the cells have same EMF, the total EMF is equal to a single EMF. Let there are n number of cells connected in C column and M row. All the cells are identical. Each cell EMF E internal resistance R. The first row is equivalent to a single cell of EMF CE internal resistance CR. Second row behaves as a single cell of EMF CE internal resistance CR. Similarly, the mth row. These are parallel combination. So the effective EMF is a single EMF. But the internal resistance effective is CR by M. Let I is the current flowing. Then in this circuit, by applying KVL, we can solve I equal to CE by R plus CR by M. I equal to CE by R plus CR by M. We are having n number of cells. So since we are having n number of cells, so n is equal to C into M. So having the LCM, then MC is N, and rearranging we get I. This I depends on M. M is the number of rows. C is the number of columns. This I depends on M. For example, if we are having 80 cells, the number of rows and the number of column, it is 1, it is 80, it is 2, it is 40, it is 4, it is 20, like this. So changing M, I will change. For some value of M, I will be maximum. That is possible. Di by dm equal to 0. Finding the derivative and rearranging, we get M equal to root over nr by r. If the number of row is this much, then the current through capital R is maximum. The internal resistance, the effective internal resistance is CR by M. Then it becomes capital R. And I maximum, that is equal to E by 2 into N by RR root over. 80 cells have to be connected so that it will send maximum current through 10 ohm resistor. Number of row and I maximum. Let this is a conductor having resistance R. This is high potential. This is low potential. Free electrons move this way. Free electrons move from low to high. We can say electrons move from low potential to high potential, or negative charge flows from low potential to high potential, or positive charge flows from high potential to low potential. Anyway, let us use the positive charge flowing from high potential to low potential. Let in time t, charge q flows this way. This q is the positive charge. So I equal to Q by T, I equal to V by R. V means V2 minus V1. V2 is the high potential, V1 is the low potential. So the charge Q enters the conductor with potential energy. The charge Q enters the conductor with potential energy QV2, leaves the conductor with potential energy QV1. So the potential energy remained within the conductor is QV2 minus QV1, that is coming QV, that is utilized for heating the conductor. So the heat produced in the conductor is H equal to loss of potential energy. Since I this much, then this H is VIT, I square RT, V square T by R. This I square RT, it is called Joule's law. This is Joule's law. The power, which is the rate of energy dissipated, power is heat by time. So power is Vi is equal to I square R equal to V square by R. This power consumed in the resistor is often called I square R loss. A cell of internal resistance R drives a current through an external resistance R. For what value of R, the power delivered by the cell to the external resistance is maximum. The power delivered by the cell to the external resistance is power equal to I square R. I we know E by R plus R. So this power depends on this R and R. Here the capital R is unknown. We will make it known with the condition power will be maximum. Power will be maximum if dP by dr or derivative of P with respect to capital R is 0. So this leads to R equal to R. That means if the external resistance is equal to internal resistance, then the maximum power the battery delivers to the external resistance. And accordingly the power maximum is, we will put R to be R here. This R will be here R, this will be also R. So power maximum is this much. Two electric bulbs marked 100 watt, 250 volt, 25 watt, 250 volt are connected in series and parallel across 250 volt. This is the printed data on the first bulb. This is the printed data on the second bulb. So from this we can find the resistance of the first bulb, and from this we can find the resistance of the second bulb. The resistance of the two bulbs, they will remain constant, but the supply voltage we can change. Accordingly the power they deliver, that also changes. So the resistance of the bulb, they remain constant. The current in the circuit is 0.08 ampere. The power expended in the first bulb is I square R1. The power in the second bulb is I square R2. The total power is now coming 20 watt, and 25 watt printed 25 watt bulb is giving power 16 watt. Printed 100 watt bulb is giving only 4 watt. Why this happens? Because the potential difference this bulb gets is 50 volt. The potential difference this bulb gets is 200 volt. Now the same two bulb connected in parallel across 250 volt. So the first bulb faces potential difference 250 volt, but is printed same it faces. Second bulb also faces the same voltage as printed. So as a result, its power is coming 100 watt, its power is coming 25 watt. So total power is coming 125 watt. Now the 100 watt bulb is brighter than the 25 watt. and the current that this bulb allows